so let's have a look at this question on cyclotron. The reason why we present this question is that cyclotron is a very important part of the Stage 2 physics curriculum, and this type of question about cyclotron and also its derivation appear in the exam every year. Okay, so it's very important for you to get a good understanding of cyclotron and remember how to do its derivations here. Okay, so let's have a look at this one. The diagram below shows a cyclotron that accelerates a particle that moves in an anti-clockwise direction. Okay, so in the diagram there, the first question asks us to explain why the magnitude of the magnetic force acting on the particle increases as the number of revolutions that the particle travel increases. Okay, so the way we're going to tackle this problem is to first think when the particle travel in the cyclotron, okay, and more specifically when the particle travel cross between the gap of the Ds, what would happen in it? What will happen to it? Okay, so we said that when the particle travels across the gap of the Ds, okay, remember that there is an electric field between the Ds, so that the particle will be accelerated by the electric field between the Ds. And it's always a good idea to have some reference of the formula here, and in this case we know that the acceleration equals to E, which is the electric field strength, multi Q, which is charge of the particle, then divided by M, which is the mass of the particle. Okay, so when the particle travels across the gap of the Ds, it will be accelerated by the electric field between the Ds. So after the particle being accelerated, okay, we're gonna say it will reach a higher speed. A higher speed right here. Okay, and also let's recall that the magnetic force in this case, okay, is proportional to the speed of the particle. Okay, that is given the magnetic field strength B, okay, and also the charge of the particle Q are constant. Okay, then therefore we know that an increase in the speed, okay, of the particle will lead to an increase in the magnetic force here. Okay, right. So with this type of question, the first thing you're gonna look at is what causes the magnitude of the magnetic force increase. Okay, so the cause, it will be the number of revolution. Then you will be think of, okay, so when the number of revolution increases, what does a particle actually do, right? So when the number of revolution increases, the particle actually will travel across the gap between the Ds for more times. Then you will think of, okay, so between the D, there is an electric field which will be able to accelerate the particle so that the particle will reach a higher speed. Okay, then we know that the magnetic force is proportional to the speed of the particle, then therefore an increase in V leads to an increase in the force of magnetic field. Okay, so that will be the first one. Second one show that the kinetic energy K of the ions that emerge at radius r from a cyclotron can be expressed as K equals to Q squared B squared R squared divided by 2m. Okay, it doesn't have to be an ion, can just be any type of particle will also follow this law here. Okay, so we have that we want to derive. Okay, so we want to derive K equals to Q squared B squared divided by 2m here. Okay, this derivation is very important. Okay, it actually appeared in past exams before, so therefore this derivation here and along with other types of derivation related to the cyclotron, for example, the period, you need to practice on this. Okay, so we want to derive this, and let's recall that the radius that a particle travels in a cyclotron, okay, R equals to mv divided by qb. Okay, with this expression here, we have the speed, okay, the speed of the particle right here. So we'll be rearrange this one to v, okay, equals to r qb divided by m here. Okay, now we have a representation of speed here. Okay, so let's think of the kinetic energy. We know that kinetic energy equals to half, okay, mv squared, and since in this case I will be able to get a representation of the speed v, I'm going to substitute v into this equation, which is half m multiplied by r squared q squared b squared divided by m squared right here. Okay, right, so this m here gonna cancel out with the m squared, the square part here, then we got 2m, then r squared q squared b squared here. Okay, so the most important parts for this question is that you should know the radius of a particle traveling in a cyclotron, and also you should know this very basic equation describing kinetic energy, and how we are going to relate those two together will help you successfully compare this, complete that question there. Okay. See, with reference to the expression derived from B, okay, so with reference, so that means we're gonna use this expression here we get from part B here, okay, state factors that affects the kinetic energy of the ions emerging from a cyclotron. Okay, so looking at this expression here, we know that for a certain type of particle, okay, or for a certain type of ion with constant Q and M. Okay, so that is once you have selected a particle, is Q and M or a constant, they won't change. Okay, then we know that K, okay, is actually proportional to, so M is constant, Q is constant, is R squared. Okay, and we know that K is also proportional to B squared here. Okay, so that means the final kinetic energy of the particle emerging from the cyclotron is only affected by the radius of the cyclotron here, and also the magnetic field strength applied on and below the cyclotron. Okay, so only dependent on R and B, which is the radius and the magnetic field strength. Okay, so some students will think, okay, does the potential difference across the Ds affect the final kinetic energy of the ion? Okay. The reason why we probably think this way is that we mentioned it before in A, that if, let's say, if the potential difference across the Ds have increased, right, that means we have a higher value of the electric field strength. Then that means the particle will be accelerated more, which means the particle will travel at a higher speed. That means it will have a higher kinetic energy. Okay, so that's the way we'll probably think about this question here. But actually the potential difference across the Ds does not affect the final kinetic energy at all. Okay, and here's how we're going to look at this question here. So let's say there would be, okay, there can be an increase, so an increase in the potential difference. Let me use delta V, so capital V here to represent the change in potential difference. Okay, the increase in potential difference right here, okay, means that the electric field, okay, electric field across the gap of the Ds will be doing more work, okay, on the particle. And again, it's a good idea to put a mathematical expression here. Okay, we know that W, okay, which is the work done, equals to delta V multiplied by Q, where again Q is a charge of the particle. Okay, so that means the electric field will be doing more work on the particle, okay, when the potential difference actually increases. Okay, and recall that, we remember that work done, okay, work done here, okay, equals to the change in kinetic energy of the particle. Okay, so that means if work done has increases, the change in kinetic energy of the particle will also increase. Okay, then as a result, we're gonna say the particle will gain more kinetic energy, okay, each time or each revolution when it travels. Okay, so that means the particle will be able to get more kinetic energy each time when it passes between the gap of the d. Okay, which also implies the particle will get more kinetic energy when it completes one revolution here. Okay, so once again we have a higher kinetic energy, that means we have a higher speed. Okay, after each revolution here, after each revolution here. So higher speed after each revolution. But recall from this expression here, the radius, okay, of the particle traveling given by r equals to mv divided by qb here. Okay, this expression tells us r is also proportional to v, which is the speed of the particle. So that means as the particle traveling at higher speed, its circular path radius will also change. Okay, so that means the particle will travel at larger radius here, okay, for each circular path. Okay, right. But recall that once we have a cyclotron, okay, the cyclotron have a certain size here. Okay, that means if the particle will travel a larger radius each time for its circular path, it's gonna travel fewer times. Okay, fewer times here. So basically, what's happening is that an increase, okay, in the potential difference actually leading to higher speed, okay, and larger v in this case, okay, larger v and also larger kinetic energy, okay. But at the same time, okay, a larger v here would also lead to a less number of revolution. Okay, so although the kinetic energy for the particle when it travels after it completes each revolution has increased, it will travel a less number of revolution when it inside the D. Okay, so it will not affect the final kinetic energy of the particle. Okay. So what we have to be careful is that the potential difference across the disk does not affect the final kinetic energy of the particle, okay? But it will increase the kinetic energy of the particle when it completes each revolution. It's just the number of revolutions has decreased, so it's more like those two effects basically cancels out each other. Okay, so in this question here, okay, we have dealt with motion of particles in electric field. Okay, so this is when we deal with that acceleration equals to QE divided by m, and we also deal with radius of the particle traveling inside of the D, inside the D's. Okay, which is this formula here, R equals to mv divided by qb, and also we deal with the kinetic energy of the particle. Okay, not only the final kinetic energy of the particle, which is this equation here, and we also come to a reason of how does the kinetic energy of the particle change when it completes each revolution if we have an increase in potential difference.